So again, to make it even more simpler, we can say let omega be 1 and k be 1. The most possible simple case that you can have. Let a be 1, or let a be half, and then omega be 1. So that would be half a meter. Omega be 1 rad per second, and then k be what? 1 rad per meter. So always make things as simple as possible when you're trying to understand something. That's called Occam's razor, right? Make things as easy as possible, and science tries to explain things the most basic, easy way that possible that you can do. So then you can say here, y is equal to cosine omega t, because the a is half, right? So then you have sine of x. So then what does that sine of cosine t, sine of x. So then what does that graph look like? Well, what do we graph versus what? When we were graphing, in other words, do I graph y versus t, or do I graph y versus x to analyze the behavior of that wave? Well, when we were graphing the traveling wave, how were we graphing things? Remember when I analyzed the traveling wave, I said let a equal 1, k equal 1, omega equal 1, and then phi is 0. Then I made it the most easiest traveling wave that you could imagine. Sine of x minus t. But then how do we plot that? Y versus t or y versus x? Right? You can actually plot it either one, y versus t or y versus x. But the one that we choose to do is we do y versus t. We do y versus x, right? Not y versus t. Because what we're trying to visualize is a wave in space and what that wave looks like. So if you graph y versus t, you're graphing you're getting rid of the x variable, so then what are you graphing? The vertical position of the wave as a function of time, where time is a dimension, you see? Right. So you're not really graphing what that wave will look like to you visually, you know?
Like 3D, three-dimensional stuff.
Yeah, you could, if you want, you could do a y, x, and a t.
Right.
That's a hard thing to do. Yeah, so then it would go like this.
Oh, yeah, that makes sense. Right.
That's a hard graph to do.
Yeah.
I have never seen one like that.
You never seen it.
You could do it.
Yeah, that's right.
Good extra credit. Right? Because time would develop like this, and then the wave would go like that, right? So it has a y and an x and a t. So the best one we do is we map the y versus x, right? So then we say let t equals 0, and then we plot different manifestations of that wave, snapshots, as a function of time, right? So we say sine of x, so then that's going to be like this, where this is going to be what? So then this is going to be pi over 2. So this would be pi over 2 meters, right? Meters. And then this would be half. 1. Right? Then you have here pi meters. 3 pi over 2 meters, and then 2 pi meters. And then this wave can keep going on like that. So this is the snapshot of the wave at t equals 0. Right? Then we said, let's take another snapshot of the wave. Let's say t equals 2 pi over 2 seconds. Right? So then what's that going to look like? Sine of x minus pi over 2. So again, since we've done this before, but now it's like you're revisiting it. It's kind of nice to see now how this chapter is similar or different than chapter 16. In other words, what's happening here? Now we're doing combination of waves, we're doing standing waves. Okay, so then what happens? So then you plot the progression of that wave later in time. Okay, so then you have here, what does that wave look like? Well, it's actually just a shifted wave, right? As you learned from trig, when you have something here, the wave has shifted by what? Pi over 2 meters, right?
Yeah.
So that means this has gone over here, this has gone over here, and every point has shifted. This has gone over here, so it looks like this. And then that means the point from the back here has moved over here. And then you keep doing that, different snapshots of the wave. Now you ask yourself, is that a traveling wave?
That's a traveling wave.
That's a traveling wave, right? Because you see how the energy is progressing? The wave is going this way. It's really weird. So the wave is doing this. Shifting to the right. But then you ask yourself, how about if this was a string? Well, would that piece of the string move to the right? No. It's actually just moving down. So it started in the middle and that element of the string just moved down. It's really weird. The concept of a traveling wave, transverse traveling wave, is that the string just went down, but the energy that it transfers moved to the right. You know? So, and then what did this part of the string do? That went down. What did this part of the string do? Let's see here. This went down, this went down, this went actually up. You see? And then this went up. This went down. This went down. So all they're doing is like this. It's kind of like the wave example again in a sports game, right? All you do is just go up and down, right? As you're making a wave, and then the wave transfers like that. And see? Okay, so now let's do the same thing with this wave, and let's see why it's called a standing wave. So let's take t equals to 0. And you have here y of x is equal to sine of x, right? So what does that mean? Then it just looks like this, you see? Okay, I'm just going to concentrate from 0 to 2 pi. Then what happens at t equals to pi over 2? So then you just have cosine pi over 2. That's going to be 0, huh? Oh, so at t equals to pi over 2, it just literally looks flat line. Isn't that weird? So it's a huge difference when the t is here and not inside of this. You see? And then what happens at, let's see, t is pi. For this t is pi would have been what? One more shift, right? So it just keeps going this way. But t is pi here is going to be y of x equals cosine of pi. So then you have -1, right? Negative sine of x, which means what? Let's see if I have a different color. Blue, red. Do you have a blue? So then it just flips, right? Yeah, let's use a blue. Okay, so that means the wave is not traveling. So it's just going up and down. There's no transfer of energy going from this to this. So how would you create this with the people in the stadium? Would you do that? Okay guys, instead of a wave, now let's cheer for our team by just creating a standing wave. How would you be able to mimic that? The wave wouldn't go around the stadium, right? It just would be standing in the place. How would you do that? The person sitting here would have to not move at all, right? So let's say this is the stadium, right? This guy says, okay, you guys, this row, actually column, right? So this column sitting all the way from here to here, you guys don't move at all. Okay, how about this guy here? You guys, this column, you just move up and down, but slightly. Okay? And this guy, you move up and down more. You see that? So you keep going like this, okay? But you guys now, I want you guys to move up and down the largest. Right? But they have to do that at the same time, right? Yeah, so you guys don't move, you guys move a little bit, you guys move a little bit, and then you go over here. Okay, you guys don't move, and so on and so forth, right? So you could actually cheer that way, but it's a lot harder to organize, right? So yes, so there's still this vertical. There's still this vertical thing going on, but no information is being carried from left to right. You see, so no information. Carrying laterally. This guy sitting here has a sad face because he wants to stand up and down, but he's not being allowed. So you just chain him up, right? This guy is happy, goes up, all the way down, crunched. Like this, like that, right? Then this guy just sits there. Yeah, so you can kind of see. And then here, you do the regular way. Everybody goes up. But that one is different. That one, this row, okay, now you get up, but you guys sit down. You get up full way. As soon as they get up, okay, now you guys get up, slightly out of phase from each other, right? You get up fully. Then you guys get up, you see? So then the information travels this way, right? So maybe you can teach a classroom of elementary school students now. Go there, show them how to make a traveling wave and a standing wave, right? With a classroom. It would be so much fun. They learn firsthand how to make a traveling versus standing. So now how do we bring this to the topic of string instruments or wind instruments? Okay. So with string instruments, since you tighten both ends of the rope, right? So they're not allowed to move up and down. So that means the length of the string has to occur at a node. And the left length and the right length have to be a node. Both, you see. So in other words, the length of the string has to be from here to here, right? So in other words, if you have a given length of string, for example, what kind of standing waves can fit there, right? So you can say, okay, if it's node and node, then this is called the fundamental frequency, right? This thing, right? So then that means half the wavelength of the wave, because the full wavelength is this, right? So this is only half wavelength. So that means half the wavelength of the wave is equal to the length of the string. Right? Then that will resonate. But then we could also have a wave look like this. Right? Then you're going to have what? The full wavelength of the wave is the length of the string. Right? Then the next one can be the next one like this. So then that means what? 3/2 of a wave length is equal to the length of the string. Right? So that means the condition, now we can generalize it again. How do we generalize that? We say lambda is equal to 2L, lambda is equal to L, lambda is equal to 2/3 L. Now, give me a general formula that will give me the conditions that a wavelength have to equal using the letter n, the integer. How do we generalize that? So this one we say it's 12 over 1, 12 over 2, 12 over 3. You see? So then we find a certain pattern so that we can write that as something with an n in there, right? So then we're going to have what? Lambda is equal to 2L over n, where what? N is 1, 2, 3. Does that fit the pattern? 2L over 1, 2L over 2, 2L over 3, right? Then we're going to flip this and solve for the required frequencies of that wave, right? So then we can say B is equal to wavelength times frequency. So therefore frequency is B over lambda. Okay? Then we have here what? F is equal to NB over 2L. Well, then that's your famous equation, right? The allowed frequencies of a wave in a stringed instrument, right? Where V is the velocity of the wave on the string over the 2L. That's the required frequencies. N is 1 is called what? Do we call it first order? These are first order max, second order max? No, we don't use that language now. Because it's not like we're looking for a pattern like of maximum minimums. Because notice, this is not perfect constructive interference. When the other topic, when two waves go like this and they meet constructive interference, then you get a constructive interference which doubles and it's a traveling wave. Here, the constructive interferences are occurring where? At only certain location of the wave. See, this is constructive interference, constructive, constructive, destructive, destructive, destructive. So it's a different topic than that other topic, right? So the constructive is here. Constructive is here, constructive is here, and we call these antinodes. That's constructive interference. And then this is node, that's where destructive interference is occurring. Destructive interference. So therefore, we can't use the language that these N's are first order constructive, second order constructive. No, it's rather the harmonics. In other words, what frequencies should the wave have so that it perfectly fits into the length of the strings, right? So this is called first harmonic or fundamental frequency. This one is called second harmonic because it's twice the frequency, right? And it's the first overtone. First overtone. Because it's one overtone above the fundamental frequency, right? And then after that, the pattern repeats. This one would be the second harmonic, first overtone, third harmonic, second overtone, fourth harmonic, third overtone, right? Then we can apply the same rules for pipes closed at both ends, because the two closed ends have to be known, okay? And open at both ends. Same rules. The only one that's different is when you have a pipe like this closed and open, then it has to be like this, node, antinode. Node, antinode. Node, up, down, up. Then antinode. In other words, what you're doing is you're making the length of the pipe either this long, from here to here, or you're making it from here to here, or you're going from here to here, so that the wave generated will have complete, it will fit nicely, it will resonate. Okay, so then what would be the pattern of generalization for that? So then what portion of a wave is this? Half of a wave?
Yes.
No, it's half of a half.
Oh, half.
It's a quarter of a wave. From here to here. So imagine the pipe is like this long. That's a quarter of a wave. See? And then if the pipe is from here to here, then it's 3/4 of a wave, right? And 5/4 of a wave. Right? Then we do the end thing. See how do we write this? So 4L over 1, 4L over 3, 4L over 5. Okay, so then can we do it this way? 4L over 2n plus 1. Right? That would work if n is 0, 1, right? Or you could do lambda is 4L over 2n minus 1, right? Where n is 1, 2, 3, 4, like that. Any pattern that could mimic what you're seeing here, you see, could work. Or you could do lambda is 4L over n, where n is 1, 3, 5, 7, 9, right? The one that we do for this one is this one, because we're not going to be calling them first order min, second order min like that again, you know, or zero central max or like that. So here we prefer to call them this way: first harmonic, third harmonic, second harmonic is missing. Okay, fifth harmonic, fourth harmonic is missing. See, seventh harmonic, sixth harmonic is missing. And see,
I have a question. I don't understand the 2n plus 1 or minus 1.
2n minus 1, it's just a pattern of predicting what these numbers, the next one will be.
Oh,
it's like the topic you learned in, I think, intermediate algebra, when you learn arithmetic sequence.
Okay.
Yeah, so this is just an arithmetic sequence, or is it called a geometric sequence? No, I think that's arithmetic when it's a certain number between them, right? So these are arithmetic series, and there's different ways to express that series. So we're just trying to see, based on what we want for that, which one should we use for our purposes, you know? And so this is the best one, you know? Then we do the solve for the frequency then, So F is V over lambda, we flip it. And we're gonna get V over 4L over N. Okay? So those are the allowed frequencies in a pipe closed at one end and open at the other, right? So this one is going to be called the first harmonic fundamental frequency. Well, that's the same thing as we did for that, first harmonic fundamental frequency. They both share that, right? But then you got the second harmonic is missing, so third harmonic. In other words, the next allowed frequency that will resonate in that tube, the next allowed frequency is 3 times the frequency of the fundamental frequency. Whereas for that one, twice the frequency will resonate. 3 times the frequency, 4 times the frequency. Here, the next frequency that will resonate is 3 times, not twice. The next one that will resonate is 5 times the frequency, 7 times the frequency. So you're skipping an octave each time, you see. So then what would we call that? Well, we can still call it first overtone, meaning it's one frequency higher than the fundamental. It's the next one, in other words. And then we're going to call the next one fifth harmonic, second overtone. That's it. In a couple of minutes, I'll probably read a little bit on it, then we're ready to start the temperature chapter. Huh. First picture of a black hole just came out.
Yeah.
Oh, wow.
But how? I was wondering how they captured it.
Well, the black hole is inside, of course, and this might be the event horizon, and then this is material outside of the event horizon, the heat generated.
Oh,
So it's probably we're using oh, it's not showing right. Very well. Oh, I just remembered this thing is not working. Dang it! No one fixed it yet, right? It wasn't working Monday either. I don't understand what's up with it. Anyone know how to fix it?